Hi guys, so good evening once again. So we are back continuing on matrices this evening. Now remember, yesterday we were looking at inverse matrix, and we were also looking at how to solve simultaneous equation using the inverse matrix method. All right, so I'm just going to recap inverse and then go straight into simultaneous equation using the inverse method. Right, so this is just to refresh your mind of what we were doing yesterday. All right, so we say in order to find the inverse matrix, there are a number of steps that we have to carry out, right? Now, an inverse matrix of A would be a matrix that when you multiply by A, you get the identity matrix or the unit matrix. So an inverse of a matrix times a matrix will give you the identity matrix, which is 1, 0, 0, 1. All right. So the symbol that we use for inverse is A to the minus 1 if your matrix is A. Now, if your matrix is some other letter, you raise it to the minus 1. So if your matrix is B, the inverse will be B to the minus 1. All right, and as I mentioned before, A times A inverse is the same thing as A inverse times A equal to the identity matrix. Now, this simply means that when you multiply the inverse by the matrix, you'll find that the law of commutative, the commutative law is satisfied. So it means that A times inverse A is the same as inverse A times A, which will give you the identity matrix. All right. So note, to find the inverse matrix, or to find the inverse of a matrix, we need to first find the determinant. And as the name suggests, the determinant determines whether or not your matrix have an inverse. So if the determinant of a matrix is 0, then the matrix has no inverse. So how do we find the determinant of a 2 by 2 matrix? First, we multiply the diagonal element, which is AD, and we multiply the other elements and subtract it from the product of the diagonal elements. So in other words, the determinant of A would be AD minus BC. All right, so you can use that as a little mnemonics to remember. After that minus before Christ, where AD runs along the diagonal from upper left to lower right hand. And then now, you know, the other two elements would go the other way. All right. All right, so inverting a matrix. Now, we use this formula to find the inverse of a matrix. We first find the determinant, and then we put 1 over the determinant times the adjoint of the matrix. So if the matrix here is A, we would find the determinant by multiplying AD minus BC, and then we find the adjoint of A and times it by 1 over the determinant. So that's a general formula. All right. Now, if the determinant of a matrix is 0, the matrix has no inverse because we cannot divide by 0. So in other words, because we have 1 over the determinant, and if we have 1 over 0, we cannot divide by 0. So the determinant will be undefined. And as a result, we cannot find an inverse for the matrix. So in this case, we said that the matrix is singular. So when the determinant of a matrix is 0, we say that the matrix is singular. Now, so singular matrix has no inverse. Now we also talk about non-singular matrix. Now, if the determinant is a number other than 0, then the matrix now will have an inverse, and so that matrix we call it a non-singular matrix. All right, so the general formula here, 1 over AD minus BC. Now remember, if we are to find the adjoint of A, we interchange the diagonal elements, so we interchange A and B, and then we change the sign of B and C, all right? And that's a formula. So just to restate, the determinant is 0, has no inverse, and the matrix is said to be singular. All matrices that have an inverse are said to be non-singular. All right, so here we have the matrix A, and you're asked to find the inverse of A. And in order to do this, we are simply just going to write this in the form A inverse equal to 1 over the determinant times the adjoint of A. So we have to find the adjoint of A, and by now you should be able to find the adjoint of A. So first, let us find the determinant. So the determinant of A can simply write as DETA would be equal to 4 times 3 minus, if you want to write 1 times 2, is the same thing as 2 times 1. 1 times 2, and that would give us 12 minus 12 minus 2. So that means that our determinant here will be 10, which is a non-zero number. So hence our matrix will have an inverse. Now to find the inverse, so the inverse of A then would be equal to 1 over the determinant. So that you would have 1 over 10 times the adjoint matrix of A. And by now we should be able to find adj A. So we interchange the 3 and the 4. So we have 3 above the upper left, and then we have 4 below the lower right. And then we change the sign of 2 and change the sign of 1. So we get -2 and -1. And this here is your inverse, but to simplify it into a matrix, you would divide each of these by the determinant. So you would get 3 over 10, you get 0.3 minus 1 over 10 minus 0.1, and minus 2 over 10 would be minus 0.2, and 4 over 10 would be 0.4. All right, so this would actually be the single matrix that represents the inverse when you simplify by multiplying by the scalar of 1 over 10, right? Now, so this is A inverse. Now, if you multiply A times A inverse, or even A inverse times A, whichever way you want to do it, because it is commutative, you will get all of this, which is 0.3 minus 0.1 minus 0.2 and 0.4 times what we have for A, which is 4, 3 along the diagonal. And then now we have 2 and 1. And once we multiply these two together, we should get our unit matrix where you have 1s along the diagonal and 0 for the remaining elements. All right, guys, so that should be clear to you. Raise your hand if you are clear on that. Guys? Okay, good. All right, good. All right, so moving along then. Now, so we know that once we multiply our inverse times the original matrix, you'll get the unit matrix or the identity matrix. All right, so here we are now going to look at how to solve simultaneous equation using the inverse matrix. All right, so we would have learned how to write simultaneous equations in matrix form. And so we would first write our equations in matrix form, which we would get this. So we take all the coefficients of the x and y, put them in one matrix, and that becomes a matrix of coefficients. Then you put the x with the y in a matrix by itself, and that will be the matrix x. Then you put what is on the right-hand side of in terms of the results, you put those in one matrix and call that the matrix K. Generally in math, we use K for constant or C for constants. All right, so in general, if we are thinking in an algebraic sense, we multiply A times X and we get K. If we are solving for X, we would have to divide both sides by A. So we divide that side by A and divide this side by A. And so this cancel. So we are left with X equal to K over A. But remember, if you take K, it would be the same as multiplying by 1 over A. So K over A is the same as multiplying by K times 1 over A. And so we know that 1 over A is an inverse of A. So we would have K times A inverse. And what this is saying to us then is that we can simplify in X, which is the matrix X. We can find the matrix X by multiplying K, the matrix K, by the inverse of A. So that's what it is saying. So X is equal to K times A inverse. Right, and this X here refers to the matrix X. This K here refers to the constant matrix of constant, which is K. And A to the minus 1 is the inverse of A. All right, so if we are to do this now, first we want to find A inverse. All right, so we'll go move along. And we'll do that. So we know that based on what we get for A is equal to 3245. And if we are to find the inverse of A, we would find the determinant of A, which is 3 times 5 along the diagonal. And then we subtract 4 times 2. So 3 times 5 would give you 15 minus 4 2s 8. So 15 minus 8 will give you 7. And so our determinant then would be 7. All right, so the adjoint of A would interchange the diagonal element, which is 5, and you would interchange 3 and 5 to 5 first, then 3, and then you change the sign of the other two. All right, so this is what we would get once we have multiplied K by the inverse. So K by A inverse would be 1 over 7 times the matrix 5, 2 minus 3, or times the adjoint matrix times K. All right. So when you're carrying out this process, what you want to do is to do the multiplication, the matrix multiplication first before you use the 1 over 7 to multiply. So when you multiply this part, the two matrices, we'll get 5 times 12. 5 12 give you what? 60. And then minus 2 times 23. Now 2 times 23 would give you negative 46. So we would have 60 minus 46, and so we'll get 14. And then we take the second row times K again. So minus 4 times 12 would give you minus 48, and 3 times 23 would be 69. And 69 minus 48 will give you 21. And so we get this one here. Now, once we have gotten that matrix, what we are to do next is just to simply divide each of these now by the determinant to get the value of X and Y. All right, so if we do that, we will get X equal to the matrix XY equal to the matrix 2, 3. And by equivalent matrix, or by equal matrix rather, we can equate X with 2 and Y with 3. So we can equate corresponding elements. X is equal to 2 and Y is equal to 3. And that would have given you the process of how to solve simultaneous equation using the inverse matrix method. Is that clear to you guys? Raise your hand if you are good with that. All right, now what would remain for you to do now is to practice using the inverse method. Now, I'm not going to give you any time to go through that because we are pressed for time and I'm going to be starting a new topic now. So I'm going to ask you that from the screenshot that you did from last class, you can just practice those questions, the first 3 questions, using the inverse method. And if you're having any difficulty with it, you let me know when we meet next class. All right, guys? But I'm going to stop sharing this slide now, and I'm going to start a new slide. All right, so our next topic is transformational geometry. All right, now I'm sure you all must have heard about the movie Transformer. Let me see the hands of those who know the movie Transformer. All right, so even as a cartoon, there is a cartoon version of Transformer. And what you know about Transformer movie is that you have cars and trucks and different automobile transform into some humanoid robots, right? Now, so transformation really is about changing shape. All right. So in mathematics, when we look at transformational geometry, we know that geometry has to do with shapes. And so what we're going to do in transformational geometry, we are going to transform these shapes. All right. So we are going to now look at the various transformation that we can carry out on different geometric shapes. All right. So for transformational geometry, if we are presented with a geometric figure, there are many things which can be done. There are many things which can be done to it. All right. Now, a transformation is a mapping that maps a pre-image onto an image. Oh, anybody understand what we mean by a pre-image and an image? Raise your hand if you understand the idea of a pre-image and an image. Anybody have any idea what that would be? Go ahead, Ms. Green. Explain what a pre-image is and what an image is.
Sir, I would say the pre-image would be like a copy of the original image and the original image.
All right, well, actually the pre-image is the original image and the image is the transform of the pre-image. You get what I'm saying? So the image that we get initially is what we call a pre-image. So whatever the images that you start off with, the first image that you start off with before you do any transformation, that image is your pre-image. And once you have done a transformation on that image, then what you get is the image. All right, is that clear to everyone? Raise your hands, guys. All right, good. So it is an operation such that each point in the pre-image has a unique image. So most of the time when we talk about points, we know that if we have geometric shapes, we're really referring to the points where the sides are connected, which would be at the vertices, right? So if every point on the pre-image, now the points that where the vertices connect, those are not the only points on the image, on the pre-image, but those are the points that we generally focus on. But right along the lines, there are different points along the lines that will also would be taken into account. Because remember, when we plot a graph of a straight line, there are many points on the line. All right? But we only need the more important lines or the more important points, which are the ones at the vertices. Because once we find those, we can connect them using a straight line. And then now we can form our image. So this is saying a transformation is an operation such that each point on the pre-image has a unique image, meaning that for every point, there's a corresponding transform point. All right, so second point would be each point in the image is the image of exactly one point. All right, that means you cannot have an image of, you cannot have a point that will have more than one image. Because if you have one point, in a pre-image, then your image must only have 1 point. Is that clear, guys? So if your image, if you have a point A as your pre-image, your image can only have 1 point, which is referred to as A dash, meaning that this is the image of the point A. So I hope that you're understanding that, guys. Now, so with that said, let us see the various types of transformation that we can carry out on different shapes. So we can do various things with a shape. We can slide the figure. Now, of course, you would have slide things around on computer screen all the time. You click on it and you drag it and you move it from one place to another on the screen. So that would be an example of a slide. Now, another name given to sliding is what we call translation. So when you slide things, the shape of the image does not change, and the orientation of the image does not change either. So it doesn't rotate or it doesn't go to any angular form. It just remains the same. So if you can recall, when you click on any object and move it around, it only slides around on the screen of your computer. All right, so that's the first type of transformation that we may look at. So that would be the sliding of images or pre-images. And so we call slides translation. All right, so the second type of transformation that we might be looking at is rotation. So rotation is when you actually spin the thing around, right? If you have a, for instance, if you have a coin and you put it on the edge. All right, give me a second, guys. All right, so so once you have the image, the pre-image, and you kind of spin it around at a using a central point, then you're actually rotating it. Now, an example of a rotation would be like the fan blade on the fan. There's a central point in the middle of the fan blade on which the fan blade is spinning. So all the blades are going around based on the fan blade on that point. So that's what a rotation is like. All right. Now, oftentimes you will have people confuse rotation with revolution. Now, whereas rotation, you have an axis on which you're spinning, revolution is when you're going around something and you maintain a certain, well, you will probably maintain a center as well, but the object itself does not spin. It rather goes around, like how you would have the moon goes around the earth. That's a revolution. So the moon is not really rotating when it's going around the earth in that center, although there is some form of rotation taking place, but we're not getting into the details of that. But the idea is that rotation, you have an axis on which to spin, like a wheel. A wheel is rotating on the car, so it has an axis on which to spin. So that's rotation. All right, another transformation that we'll be considering is the the change of the size of an object. Now on the computer, we are on your phone. If the object looks a little bit too small, you would do a little zoom in. And zoom in is really enlarging the shape, right? So that you can have a bigger picture and clearer picture of what is really happening. So sometimes you might zoom it to get it bigger. And if it is too big, you might zoom it down to get it smaller. When you zoom it down, you're really reducing its size. So we refer to this form of transformation as enlargement or reduction. So once you're making the object bigger, by increasing its size, it would have been an enlargement. And if it is you're making it smaller, then it would be a reduction. Now in enlargement and reduction, the proportions of the sides remain the same. So once you zoom it up, everything increases in size proportionately. And if you zoom it down, everything decreases in size proportionately. So that's what your some other things to bear in mind. So the orientation, meaning that you don't flip around the shape or anything like that. The orientation remains the same. It's either it gets bigger or it gets smaller. All right, so the next one we'll be looking at will be reflection. All right, and reflection would be something that you can relate to a mirror. When you look in the mirror, you see a reflection of yourself, but the image that is inside the mirror appears to be the same distance away from the mirror as you are in front of the mirror. So a reflection will have those kind of properties. Now the object would not change in terms of size unless you go further and further away from the mirror. So whatever size you are when you're outside the mirror, you maintain the same size when you're inside the mirror, or your reflection is inside the mirror. All right. So these are all the different types of transformation we'll be looking at. So in each case, we say that the original figure has been transformed, and the original figure is really the pre-image, and the image is what you get after the transformation. All right, so in terms of you have an original figure and you zoom it up, then the bigger zoom now would be the image of the original image. All right, and so the original image is what we call a pre-image. All right, so point 2, an object that undergoes any of the above operation is transformed, and the operation is called transformation. All right. Now, definition: the pre-image is the original figure before transformation. The definition again: the image is the figure after transformation. Now, if triangle ABC is the pre-image, then triangle these should have been dashes, not really what you call apostrophe. These are dashes, right? So just make a note of that, guys. All right, so our transform image, we generally write